Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 15, BGP Part 3, as we continue our in-depth analysis of the Border Gateway Protocol to get you ready for exam success and real-world success. We're going to start that off by something that does get in the way of real-world success quite often, and that's the rule of synchronization. I'm not really talking here when I say synchronization on the whiteboard about the synchronization, say, between OSPF routers, where they have to synchronize their databases. We're not really looking at that. BGP has a rule of synchronization that is on by default and is usually turned off, but for the exam and the real world, you need to know what the rule is, and it's the kind of thing where when you read the rule, if you don't see a good example of it or you don't see it in the real world, it's not going to make a lot of sense to you. So we're going to show you a really good example of what would happen with synchronization under certain circumstances. And we're going to move into, from there, a discussion about BGP full mesh deployments and the iBGP route advertisement rule. Now, before you roll your eyes at that route advertisement rule, you already know what that is. That's just referring to the rule that says that if a router has two iBGP peers, it can't learn a route from one and then advertise it to the other. We're going to see how that ties in with BGP full mesh deployments. We'll talk about the pros and cons of full meshes. We will talk about how to figure out how many different connections you're going to need depending on the size of the network. There's a great formula, very simple formula for you to figure that out. And that's going to lead us into a discussion about route reflectors and clusters. Route reflectors are everywhere in BGP deployments. So you've got to know what you're looking at with a route reflector. Not only do you have to know how to configure one, which is simple, but you need to know what routes route reflectors are going to reflect, which ones they're not, who they're going to reflect it to. You got to know all that, and you will. Finally, in this video, we're going to take a look at prefix lists. This is another different kind of list for you, and it's a way to filter BGP routes. And you'll see that when it comes to that, we have several different choices, but Cisco recommends you use prefix lists. Cisco's not always right, but they're certainly right about this one. I recommend it too. I've done it in production, I've done it at the IE level, and I'm telling you, prefix lists are the way to go with that. So let's get started then with our discussion of the rule of synchronization. And a little background here before we actually hit what's on the whiteboard. You know now, of course, that BGP consists of iBGP speakers and eBGP speakers. But iBGP routers have several special rules that differentiate them from eBGP routers. And you've got to know these rules. We've talked about iBGP neighbors don't have to share a physical connection. They have so far in this course. But what we're going to look at later is configuring them the way Cisco actually recommends them to be configured, and that's using the loopback interfaces to peer rather than physical interfaces. We will talk about that later in the course. What we're going to look at right now, though, is the situation that iBGP routers do not send updates to every single neighbor. They don't do it. There are only 3 circumstances under which an iBGP peer will advertise a route to a neighbor. And the first one is if it was created on the local router with the network command, and you've seen the network command in action throughout the BGP course. Whether it's in there via route redistribution, either by redistributing static or IGP routes. Or third, if the advertised route is a connected route to begin with. So that's a good list of rules to keep memorized for your exam, and that's fine, but what does it all mean when we just put all this stuff together? What does it really mean? What it means is that when an iBGP speaker learns about a route from one iBGP neighbor, the only peer that route can then be advertised to is an eBGP peer. Now, in theory, that would require a full mesh, and I mean a full logical mesh. And maybe that wouldn't be so bad. Then again, maybe it would be. And we're going to discuss that in just a few minutes when we're done with the rule of synchronization. And let's take a look at what the official rule of synchronization is. We've beaten around the bush long enough. Here it is. The rule of synchronization in BGP states that a transit autonomous system will not advertise a route learned from one eBGP peer to another eBGP peer until all the routers in the local autonomous system have learned about the route. Now let's just be real honest here. If you haven't seen it in action and you read that rule, you're trying to memorize that for exam day. Well, we want to get past that. We want you to see what it's all about, and we're going to look at it in just a moment. But synchronization isn't always a concern, the rule of synchronization. Both of these factors have to occur for synchronization to even be a concern. First off, the autonomous system has to be a transit AS in the first place. And secondly, there have to be non-BGP speakers in the transit area. And that does happen because sometimes we're not always going to configure BGP on every router in a transit area if we don't think we have to, because BGP is a resource hog. So there will be very, very certain circumstances where we have to worry about synchronization. And we're going to look at an illustration of one in just a moment. But if we look at those two rules, then that means that there are a lot of circumstances under which synchronization can be turned off. And synchronization can be turned off in any one of these three circumstances. The first one being all the routers in the AS are running BGP to begin with. If every router in an autonomous system is running BGP, synchronization is not a problem and it can be turned off. If a full mesh exists in the autonomous system, a full BGP mesh, then synchronization can be turned off. And then finally, if the AS is not a transit autonomous system in the first place, synchronization can safely be turned off. And it often is. Let's take a look at a situation where synchronization, though, would rear its ugly head. Here we have router 1 in AS100, and it's connected to a network 220.0.0/16, and it wants to advertise that and make sure that router 5 can reach it. Router 5 is on the other side of our network here, and it's in AS500. The only way for the data to get there is through AS200, which makes AS200 a transit area. So now we need to look at synchronization because we have a transit AS. And I'm going to bring the rules back up. Synchronization is only a concern when first off the AS is going to be a transit AS. So that's true of AS200 in this situation. Is the second part true? There are non-BGP speakers in the transit area. By an amazing coincidence, yes, that is also true. Router 3 is not speaking BGP. And you can tell by looking at this drawing, because if it were, you'd see some peerings to it, but you don't. So in this situation, then, we have to be concerned with synchronization because the rule of synchronization is in effect. Because router 1 is going to advertise that connected router, that route, into BGP with the network command. The advertisement will go to router 2. Router 2 will then send the advertisement to router 4. But router 4 is going to realize that it's connected to a non-BGP speaker and that this path was originally learned from an eBGP peer. And at that point, router 4 will not advertise that route to router 5. Why not? Because there's no possible way that router 5 can send data successfully to 220.0.0/16 because it's a BGP route. Router 2 will see it and have it in its routing table, and so will router 4. But router 3 can't have it because router 3 is not speaking BGP. Now, and if you're in a hurry, you may look at this and say, well, router 4 can send, sure, router 5 can send data to 220.0.0 because it would go to router 4, it sends it across the iBGP peering to router 2, and then to router 1, and then down to the network. That cannot happen. And that's where you have to watch the network diagrams. You have to watch what they give you. You have to watch what you read out there in the real world too. This iBGP peering is just that. It is a logical peering. Data's not going to go over the logical peering. It's got to go over a physical connection, which we've got here with our little serial symbols, our little lightning bolts, if you will. So what would happen if router 5 had a route for network 220? It would send it to router 4, and router 4's only possible choice then is to send it to router 3, and router 3 doesn't have a path to 220.0.0 because it's not a BGP speaker. It drops the packets. This rule of synchronization does get a bad name, and sometimes among Cisco certification candidates and among real-world BGP workers. But the truth is, this is actually helpful, because if synchronization, the rule of synchronization did not exist, then what would happen is that router 4 is going to waste its time and waste its resources, more importantly, sending updates to router 5 in the first place for data that can't possibly get to network 220. And then router 4 is going to have to spend time routing packets destined for that network that can't possibly get there. So it's still a waste of router resources. It's not just that data can't get there. So, most deployments, though, in the real world, you are going to see BGP synchronization turned off. I actually have it turned off for our route reflector discussion that's coming up, because you'll find in a home lab, right after you type router BGP and then the AS number, you'll find yourself subconsciously typing no synchronization. So let's take a look again at those rules. Very much worth reviewing. You know what the rule of synchronization is now. You have to know when it's a concern, and both of those factors have to be in play for synchronization to be a concern. The AS has to be a transit AS, and there are non-BGP speakers in the transit area. But if any of those bottom three rules, I shouldn't say rules, factors are in effect, then you can turn synchronization off. And you may ask how we do that. I'll just actually put it right here. Just put it right under the BGP configuration. I've done that for a couple of routers here in the course. And you just simply type no synchronization or no sync under the BGP process. And that's it. So now that we've nailed the synchronization rule, and I expect you, any question they ask you on the BSCI exam, I expect you to get correct regarding synchronization. It's not going to bother you at all. Well, let's take a look then at BGP full mesh deployments and why they may or may not be a good idea. And what we have to be concerned about, and we're talking about a full logical mesh here. We're talking about, say, 5 or 50 or 500 routers, all having a logical peering relationship with every other router in the AS. Now that sounds like a bit of a nightmare, and actually it is. So why are we even thinking about it? Because of BGP split horizon. And you thought you'd gotten away from split horizon, right? Wrong. But that is actually the correct term for the rule that states that one iBGP peer can't learn about a route from one iBGP peer and then advertise it to another. I know you're tired of hearing that by now, but it's very important. And that is actually BGP split horizon. So split horizon with BGP is far different than the split horizon that you came to know and love in your RIP, in your EIGRP, and your IGRP studies. So this rule would require us then to have a logical full mesh among all iBGP speakers in an autonomous system. Okay, big deal, right? Big deal. Why do we want to avoid that? Well, the official reason, and a very good reason, is on the board. It's because of the hit on your router resources. And there's a formula for determining how many connections are required for a full mesh. And I actually just saw this on the group study CCNA mailing list. Someone was asking about this. This is a formula, not just a BGP formula, but a formula that you can apply to anything where you're looking at a full mesh. And here, the formula is x times x minus 1, then divide that by 2, with x being the number of routers involved. So that means that a 20 router full mesh with just 20 routers in it, you're looking at 190 separate TCP connections. Because you've got 20, put in 20 for the x, both places. 20 times 19 is 380. We divide by 2, 190. That is a lot of connections. That's a lot of overhead that we don't want to spend. Now I'm also going to give you the unofficial reason, and I alluded to it earlier. It's an administrative nightmare. And it's very easy just in a home lab environment to have maybe 3 or 4 routers and you mess up a neighbor statement here or there. And you spend a little time trying to figure out which one you missed or what IP address you misentered, and it takes up some of your time. Can you imagine creating that many separate TCP connections, that many separate peering connections? I'm not calling any of us lazy, but I am saying we've got better uses for our time. Because there's no one who can create that many neighbor statements and get them all right the first time. Then you got to go back, find out which one you're missing, run show IP BGP summary a bunch of times. So again, there are several reasons to avoid full mesh deployments. First off, we've got a lot of TCP sessions being created on an unnecessarily large amount. And those sessions, hey, that bandwidth adds up. That bandwidth adds up. And then finally, you're going to spend a lot of time, first off, writing that configuration. Sooner or later, you're going to miss one, and then you get to spend more time even troubleshooting it. So it's a bit of a nightmare, but there is a good workaround. It's not really a workaround, but it's a way to defeat the split horizon rule, and that is route reflectors. Route reflectors are the exception to our BGP split horizon rule. Because when we configure a router as a reflector or an RR, as you see it in a lot of documentation, then they can learn a route from one internal BGP peer and advertise it to other internal peers. And it's a huge time saver for us, as well as being more effective overall than a full mesh. Because the clients don't even know this is happening. The clients are the routers that are configured to send routes back and forth between themselves and a route reflector. And they don't even know it's happening. And the great thing is, you don't even have to visit the clients. You don't even have to connect to them or go to them physically, because they require no additional configuration. And let's look back at the situation we were talking about before with a full mesh. We talked about the hit on the router resources with a full mesh. We talked about how it takes extra configurations to do that, obviously. We talked about the additional troubleshooting that may become needed. But another key here is that when we configure a route reflector, we only have to configure the route reflector. We don't have to connect to 20 routers or 50 routers or however many routers are going to be clients. We've only got to configure the route reflector itself. But it is possible for a BGP speaker to have a peering to the route reflector and not be configured as a client. We have a really clever name for these. We call them non-clients. And for total connectivity, though, those non-clients would need a TCP connection to every other router in the autonomous system. Where, of course, if it's a route reflector client, the only peering it's going to have is back to the route reflector. Again, revisiting the formula that we talked about earlier. In a 20 router full mesh, according to this formula, we would have 190 separate TCP connections. That's a lot of typing, that's a lot of visiting 20 routers, that's a lot of telnetting, it's a lot of walking, it's a lot of work, and then when you're done, it's a lot of overhead. And hopefully you got it all right, because then if you didn't get it all right, it's a lot of troubleshooting. So when we configure the route reflector, though, the only connections we have on the clients are back to the reflector itself. The clients don't have connections to each other. So if you've got a BGP route reflector in the middle of a 20 router AS, you've got 19 connections going out from the route reflector and 19 coming back in, one from each of the other routers. That's only 38 connections. So that's a tremendous amount of savings in time, in typing, in troubleshooting, and in bandwidth. Let's look at a scenario where a route reflector may come in handy. And you may be able to look at this particular network and see, is there a potential problem when we advertise a route over from router 4, because that's what we're going to do. And you can see in AS 1235, router 1 has appearing to routers 2, 3, and 5, but there is no full mesh. Now you could probably look at this and say, okay, you know, I've got a pretty good idea that router 1 is going to be a route reflector here, because after all, we are talking about route reflectors. And if you've done some previous studying, some previous reading for the BSCI exam, you could look at this and say, well, you know, I know where the route reflector is going to be, and I know the command to make it happen, so, you know, okay, I got this. But, you know, that's not what we do in this business. And I want you to be prepared not just for the exam, although that's obviously important. You're gonna kill the exam. You're gonna do very, very well on the exam. I want you to be effective with this in the real world too. And when we go to a client site, or let's say for our employer, we just rolled out, you know, a little BGP deployment, we're not going to have multiple choice when things go wrong. That's why I tell especially CCNA candidates who are a little nervous, you know, about touching the routers for the first time, say, you know, you got to get in there. Because when you're configuring a router and something goes wrong or not quite doing what you thought it would do, we don't have multiple choice here. Let's look at this cursor. There's no multiple choice on that screen. We have a cursor and a command line, and that's it. So we have to analyze what's going on and then apply our knowledge to it. It's double A. You analyze and then apply your knowledge. And that's what you're going to do as a CCNP, and should you pursue the CCIE, that's what you're going to do there too, because the CCIE is not a test of memorization, it's a test of your analytical skills. And so is this, because what we're going to do is look at this network that's been configured. This is already set up, and by the way, the network number that I'm using here is 10110 with the router number serving as the last octet, because all 5 of these routers are on a single Ethernet segment. Those are the only interfaces we're using. Now I left that out because we're concentrating on the peerings. But when we see the next hops, you'll see they're all on the 10110 network. So next hop should not be an issue here. But what we're going to do is look at this scenario and say, okay, if we've got the network 4444 being advertised into BGP on router 4, what do we expect to see downstream? And if we don't see what we expect, what are we going to do about it? Because that's what we do in this business. And that's what you're going to do on the exam too. You got to look at something like this and analyze it and apply your knowledge. So if we are advertising a network on router 4 into AS4, do we expect to see it on router 3 to begin with? I think it's a pretty safe bet that we do. That's an eBGP peering. They are not in the same AS. And we run show IP BGP, and we see the route, and we also see the asterisk and the arrowhead. So you know that this is a valid and best route. So that's the easy part. We know that one's valid. We see the next hop of 10114. Let me ask you a couple of questions now. Will router 1, which is also a peer of router 3, see this network? Will router 3 see the network? Will router 1 see the network? If it does, will the route be valid and best? And also, what will the next hop IP address be for that route? If you could tell me all 3 of those things, you're really doing well. First off, let's see if router 1 sees the route to begin with. Yes, it is there. So far, so good. And you know now we're always looking for the asterisk and the arrowhead. We see it there. valid best route, no problem. It's usable path. The next hop's a little odd though. 10114. Let's take a look at show IP BGP 4444. And let's leave the extra dot there off the end. So here it is. And if you're really eagle-eyed, you can see one other issue right now in this command. And that's why I love running this command. You can really see what's going on. Right now we're concerned about the next to last line because we can see that the route is coming from 10113. That's router 3's Ethernet interface. So if that's the case, what's this? It's the next hop IP address, 10114. Why is it 10114? Why isn't it 10113? Is something wrong? Did something go awry here? No, nothing went awry. Router 3 learned the route from an eBGP peer and then advertised it to an iBGP peer, and in that scenario, the next hop IP address is always retained. That's not going to be a huge deal here, but it could be in a larger network, and it's also really good to know for the exam. You got to know why that next hop IP address is what it is. So far you're doing really well, and you see now that we can take a structured approach and not just say, okay, yeah, router 1's a route reflector and leave. We have to know everything else that's going on here. So the next logical question is, will routers 2 and 5 see that particular route? If they do, what will the next hop be? And is it a valid best route? Those are the questions. Let's go over to router 2 and get ourselves some answers. Well, we're not getting anything from the show command, and when a Cisco show command doesn't show us anything, there's nothing to show. So it looks like the table's empty. But you know what we ought to do here? When we don't see any routes at all, we ought to check and make sure the adjacency is up. We never want to assume that. And yeah, it's up. I ran show IP BGP summary, which gave me the summary of the neighbor relationship. And you can see in the next to the last column going from left to right, the up down, it's been up for 12 minutes and 38 seconds. So that's not the problem. Let's go over to router 5. We see this adjacency back to 10111 has been up for about 13 minutes. So the adjacency is not the problem. I think there's another problem. And maybe you've already nailed it. I bet you have. BGP split horizon. Remember, split horizon in BGP is a totally different animal than it is with the IGPs. And the case here being, router 1 learned about this network from an internal BGP peer. Therefore, by rule, it cannot advertise it to other internal peers. That's the problem right there. Let's take it a step further. We always want to go to the next level here. Let's add some networks. We're going to add router 2's loopback with that command, the network mask command. Let's go up to 5. And we're going to add router 5's loopback. We'll do a quick clear soft here. I should have done that on 2, but I bet it's already taken effect. Let's go over to router 1 and see if it sees those 2 routes yet. If it should. And it should, and it does. And they are all marked valid and best. So they're all fine. Will router 2 see router 5's loopback? Will router 5 see router 2's loopback? Will router 3 see either one of those loopbacks? Let's see. Let's go to router 2. Looks suspiciously the same as it did before, right? Let's go over to 5. Looks like it did before. It's still not learning any of the other routes. And router 3's looks exactly the same. The issue again, BGP split horizon. Router 1 is learning about router 2 and router 5's loopbacks from internal peers and therefore cannot advertise them to another internal peer. So right now BGP split horizon is running our network. But we're going to take care of that by configuring a route reflector, but we do have another option. What's the other option if for some reason we could not make this a route reflector? What could we do in AS 1235 to resolve this issue? We looked at two solutions. We looked at route reflectors and we looked at full meshes. We could create a full mesh in AS 1235. And one question always leads to another in Cisco. Welcome to Cisco certifications. When you answer one question, it creates two more. If we create a full mesh in AS 1235, how many separate TCP connections will that require? I know you remember the port number too, right? Port number 179. How many separate TCP connections will be required in AS 1235 if we don't use a route reflector? Remember that formula? X times X minus 1 divided by 2. And here X is 4 because that's how many routers we have in the AS. 4 times 4 minus 1 is 12. That's 4 minus 3. Excuse me, 4 times 3. And we divide 12 by 2 gives us 6. We would need 6 total TCP connections to make this work with a full mesh. We're not going to do that though. We're going to configure a route reflector because another problem with a full mesh, as opposed to all the other problems I've already told you about, is that it's not a scalable solution. And that's a bit of a buzzword, but here it really does apply. Because in the future, we could add 4 new routers to AS 1235. Well, then we've got 8 times 756 divided by 2. We're going to have 28 separate TCP connections for a full mesh. If we have a route reflector configured, we only need to go to the route reflector and write 4 more lines and make the other 4 routers clients. Actually 8. We would need peerings and then the clients. So a route reflector is a much more scalable solution than just trying to keep up with a full mesh. Even if you know which router is going to be the route reflector here, and I'm sure you do, it's router 1. It's the only one with peerings to all the other routers in the AS. And even if you know the command, which is actually the easy part of this whole thing, you may be surprised at something you see here when we configure 3 route reflector clients on router 1. This is something that a lot of books, videos, documentation on a lot of and other products just leave out. But we're not going to leave anything out because I want you to see it right here. This is the command to configure router 2 as a route reflector client. It is simply route reflector client with the dashes at the end of a neighbor command. When you're first learning these commands, I would recommend that you type them out. I could have typed route-r here and hit enter and it would have taken it because only one command matches that syntax. But I don't like to do that when I'm teaching, and I don't think you should do that when you're learning it, because you will be amazed at how well you retain these commands on exam day when you've actually typed them out instead of abbreviating them. So let's see, we're going to make 10112 a route reflector, and then 10113 a client. Hey, look at that. Look at that message right there. Adjacency change 10112 down RR client config change. I wonder why that happened. Well, actually, I just told you why it happened. Well, now 10113 is down. How about 10115? Those are the 3 clients. Wow, look at that. When you configure a remote router as a route reflector client, the adjacency is going to come down. It is not a soft reset. It is coming down. That's a kind of important piece of information, wouldn't you think? I I very rarely see this in BGP documentation, books, training videos. I don't know why. But this is what's going to happen. So you need to be prepared for that, especially if you ever do this in a production network. Because as you know, BGP tables don't rebuild immediately. And also some BGP tables, as we're going to talk about in the next video, they can hold thousands and even tens of thousands of routes. So this is a very important piece of information for the exam in the real world. And when you configure a device as a client, you should expect to see the adjacency go down. So that's what happened here. While we were chatting, they came back up 2, 3, and 5. They're going to be down for about 25 to 30 seconds, plus some time for the tables to be rebuilt. So let's make sure that our adjacencies are fine. They should be. We're always going to double check that. And we see the adjacencies here are all up. And you see now the up-down timers are just around a minute because that's about how long they've been up. Let's go to routers 2 and 5 and see what we see as far as the routes go. Now router 5 has the routes for 2 and 4, their loopback networks, and they are marked best invalid. Since they're all on the same Ethernet segment, the next hop is not an issue. But the only way router 5 could ever see those routes is to be a route reflector client. And we'll go around the network here. You see router 2 sees all 3 of the routes, and they are all marked valid and best. Router 3 sees all 3 of the networks, and they are valid and best. And finally, let's go out to router 4 and see what we see out there. Yep, they're all valid and best. So all 3 networks are now seen by all 5 routers. But as we applied our knowledge, we saw why the next hop addresses were what they were, especially when router 3 was advertising in the router 1. And you could see that the only way we had connectivity was by having a route reflector or a full mesh. So route reflectors really serve 2 major purposes. First, they're going to reduce the number of TCP connections needed in an internal BGP deployment, which is what we had here, a 4-router deployment. And that's fantastic. But another benefit is that they allow us to circumvent the BGP split horizon rule. And as I mentioned a couple times, one answer always leads to another question. We're always digging in this class. We're always going a little further. So, if BGP split horizon is there to prevent routing loops, and route reflectors help us to work around split horizon, why don't we have routing loops for them when we're using route reflectors? How about that? Why don't we have loops? Because of clusters and the originator ID attribute. And what a BGP cluster is a combination of route reflectors and their clients. And I did say route reflectors because you can have more than one route reflector in a cluster. So right now, AS1235, that is a cluster. Router 1 is our reflector, and 2, 3, and 5 are the clients. And what happens is that the originator ID attribute identifies the router that originated the route in the first place. And this attribute is set by the route reflector, and it effectively eliminates the chance of a routing loop, because if the router that originated the route sees that same route in an update, it's going to be discarded. So the originator ID attribute really helps us out when we basically work around split horizon. We don't disable it because there is no command for disabling BGP split horizon. So that's why we don't have routing loops when we use route reflectors. Now, I mentioned to you earlier that there were some specific rules about how route reflectors handle routes depending on who they came from. And these are very important to know for the exam, certainly, but also for real-world troubleshooting. Because you could see just in this scenario that we walked through that if you really didn't know the theory, if you really didn't know what was going on, you'd be kind of puzzled about these next hops. So we need to know, to what routers do route reflectors reflect routes? Where are they sent? Well, an update from a route reflector client will be sent to all client and non-client peers. An update from an external BGP peer will be sent to all client and non-client peers. See a pattern here? I think you do. And finally, though, if a route update comes from a non-client peer, that route is reflected to all clients in the cluster, but not to other non-clients. That's the difference between being a client or a non-client, is that if an update from a non-client peer will be successfully reflected to all clients, but will not be sent or reflected to non-client peers. Good stuff to know there. And now that we have our full BGP connectivity throughout the autonomous systems in our current network, we need to look at scenarios where perhaps we don't want a router to get all the routes that it sees in its routing table, in its BGP table. Perhaps we want it to have some routes, but not others. And that's where the use of prefix lists comes in. And Cisco recommends prefix lists for filtering BGP updates. So do I, as opposed to trying to write an access control list to filter them. That's not always the easiest thing in the world to do. And you'll see that prefix lists, once you get used to the syntax, they're very easy to work with. Among the reasons that Cisco documentation gives, the official reasons for using prefix lists, good stuff to know: the support for incremental updates, their high flexibility, and that writing BGP prefix lists is much easier than writing ACLs that filter BGP updates. And again, I can vouch for that from my personal experience in both production networks and real world and labs. It's a lot easier to write a prefix list to get the desired results. And you're going to see that a prefix list has a lot in common with an access control list. If a route is expressly permitted, it's going to be used. If it's denied, it's not going to be used. Makes perfect sense, but it is, again, the basic ACL theory as well. All prefix lists have an implicit deny at the end, just like an access list. And therefore, if a prefix is not expressly permitted, it is implicitly denied. Now, prefix lists work from top to bottom, just like access control lists. And when a match is found, the list stops running. And of course, as we've just mentioned, we have the implicit deny at the end. For the exam and for the real world, keep in mind that explicit deny statements do not override the implicit deny statement. You probably saw one of those depending on whose practice exams you used for the CCNA prep, where you'd see a question with a 3 or 4 line ACL that says, what's being denied by the following ACL? And you would see only deny statements. And the truth is there that everything was denied, because 4 things would be expressly denied, and then finally the implicit deny would deny everything else. The same is true for a prefix list. So we better know how to write a permit any statement in prefix list language, shouldn't we? That's a good idea. And you're definitely going to see one of those in the network configuration we'll be running in just a minute. Just a little more theory for you. Prefix list statements are numbered, and this is fantastic, because if you have tried to move access list lines around or add a line to an existing ACL, sometimes you can do it, but most of the time you just end up overwriting what you wrote before. You can't go back to a standard ACL in most cases with most iOS versions and just stick something in the middle and say, oh yeah, I meant for this to be the 5th line of this 10-line ACL. Doesn't work. But with prefix lists, you can, because they are numbered, and they're actually numbered by default. The lowest number is going to be at the top. It's going to look, 5, 10, 15, 20, because if you don't number the lines, they increment by 5s by default. And you'll see that in just a few minutes. So the lines are going to go 5, 10, 15, 20, and onward. the line with the smallest sequence number that matches the prefix will be the line that applies a permit or deny against the route. And of course, those lines are going to be at the top because the lines will appear in numeric order. So we would expect to see, just like in ACL, that it's going to run from top to bottom, and as soon as a match is found, the prefix list is going to stop running. To show prefix lists in action, we are going to use the same network that we used earlier in this video, and there's been a little bit of an addition. Just to bring the drawing up first. The router 1 is still acting as a route reflector. Everything else is the same. And while router 4 is still in the picture, we're really going to concentrate on the routers in AS1235 to see prefix lists in action. What I have done on router 5 is added 4 networks. I added 4 loopbacks. They are 16.111, 17.111, 18.111, 19.111. And they all have 8-bit masks. You're going to see that in action in the tables in just a moment. And I used the network command to put all 4 of those routes in. So let's take a look at router 5's table first at this point. And you see 5 routes with a next hop of all zeros. That indicates that it originated locally. We see the 4 new networks over there, 16, 17, 18, and 19. And we also see that weight. Don't forget that default weight for locally originated routes is 32,768 as opposed to 0 for all other routes. So just like we did before, let's go downstream and see what routes are in the table and make sure they're valid and best, which these all are. So router 1 sees all 5 of the routes coming from router 5, and router 1 is still configured as a route reflector client, a route reflector. What I want to show you is that you can actually see with the show IP BGP extended command, you can actually see when routes come in from a route reflector client. Good piece of information to know. So we would expect then routers 2 and 3 to be receiving these routes from the route reflector, and it is, and they are shown as valid and best, so everything's fine there. We'll go down to router 3, and everything shows up fine there. So that's as far as we're going to go with this. We're not concerned about router 4 right now, but we do see that we have successfully added 4 networks to our BGP configuration. We have the 1 network we had before, the all 5's loopback, and then the 4 additional routes. So let's say that we are looking at our network here, and we want router 1 to see the more specific routes that it's seeing now, but we don't want routers 2 and 3 to see the new networks. For whatever reason, could be security, maybe just somebody on R1 needs to know about it. Doesn't matter why, we just need to be able to do it. We want routers 2 and 3 to keep the route to the all 5's loopback, but we don't want R2 and R3 to have the routes for networks 16, 17, 18, and 19. This is where a prefix list comes in. And as you climb the ladder of certifications, as you head for that IE, as you head for the mountaintop, you will see other ways to filter BGP routes, but this is by far the most common, and it's the one we really need to nail for the BSCI exam. So I'm going to bring the rack back up, and what we're going to do is write a prefix list on router 1, because if we put them on router 1, that's where the actual filtering is taking place. We don't want to filter them on 5, because if we filter them there, then router 1 won't see the network 16 through 19. So let's go up to router 1 and write our first prefix list. And the command to start a prefix list is IP prefix list. And we're just going to call this no 16 through 19. We're going to make it a deny statement. Let's use iOS help here to see what our options are. Deny description, permit, and sequence. Those of you who got your CCNA training from me know that I'm a stickler about describing what a prefix list does or an access list does, so those who come behind you will know. I've always found it a little funny that they misspelled description there. When it says prefix list specific description, they left an O out. But I've misspelled words too in my life. The ones we're really concerned about right now are deny and permit. But notice that there's an SEQ there for sequence number of an entry. And that allows us to go back into an existing prefix list and add a line in the end, at the end of the prefix list, in the middle, in the beginning. It's up to us. But we're going to leave the sequence number out of this prefix list so you can see what the default is. So the first thing we're going to do is put a deny in. And now let's use iOS help. And we're even going to get some extra help here, I think maybe because Cisco's technical assistance people finally got tired of getting called about this. It actually shows you the syntax of the prefix list command. That's not going to be helpful on the exam because it probably won't be in front of you, but you will be able to see this in a production network. IP prefix list, and the name of the list, then a deny statement, and we're going to put in 1600/8, and that is attached there at the end. And I'm going to use my up arrow so I don't have to do all that typing, and just use 17 right there. I'm going to use my up arrow again to repeat the previous command. Go in and change that to 18 and 19. I am not done though, because while I want to deny these 4 networks from being advertised to these 2 neighbors, I want to permit everything else, which right now is just one network, 5555. So I have to put in the equivalent of a prefix list permit any statement so that the implicit deny is never read. Here's the syntax for permit any in a prefix list. LE less than or equal to 32. So by typing that line in, that means the implicit deny, the implicit deny will never be read. These 4 networks will be denied, and everything else will be permitted. So now I need to apply it. And let's do that. Let's go back to 1. We're done there. Let's see if we can take a look at that list before we apply it. Yeah. Show IP prefix list shows me the ACL that I just wrote. Shows me the name of the prefix list. Shows me the name of the prefix list, how many lines are in it, and notice the sequence numbers. So now if I say, I miswrote that and I need to put another statement in between 5 and 10, then I could call it sequence number 6, 7, 8, or 9 when I wrote it. We'll actually go back and do that when we're done seeing this in operation. But that's a big help for those of us who have written long ACLs and then said, oh, I didn't know such and such was going to happen. Now I got to rewrite the ACL. You don't have to rewrite a prefix list from scratch. So now that we have written it, you see the syntax. You now are going to see how we're going to apply it. And we're going to go back to the neighbor statement. So the neighbor statement isn't just for making adjacencies, it's for just about everything else. Looking at all those options again, the one we're interested in right now is prefix list. Filter updates to or from this neighbor. So it sounds to me like we got to indicate some direction here at the end, huh? Prefix list, no 16 through 19, out. And then with my up arrow, I will cursor in and apply that to router 3 as well. Notice my adjacencies didn't come screaming down the way they did when we configured a route reflector. So all that's fine. We're going to go down to router 2, see what the impact is on the table. And you see now already the filtering's taken place. Router 2 is still seeing the all fives network, but it no longer sees the other 4 networks we put on. And router 3 is going to be the same way. Right? Right. It sees router 5's original loopback, but then when we put the other 4 networks on and then filtered them at router 1, the routers 2 and 3 are no longer seeing the networks in question. Let's go back up to 1 though and make sure that they're still there, and they are. So what we did again successfully with that prefix list, router 5 was advertising 5 networks over to router 1. We decided that routers 2 and 3 should only have access to the original one, the all fives loopback. So we wrote a prefix list expressly denying those 4 newer networks, and then we wrote a permit any statement at the end, which let everything else through. If we had wanted to then expressly permit 5 and then deny everything else, well, we could have just written it, permit 5555/32 and then just let the implicit deny take care of business. So let's again assume that we have written this list and we've applied it. And oh, you know what we meant to do? We meant to permit the network 16100/16, but still deny all other networks in that subnet. So what we could do there is just add to the same list and let's use our iOS help to show us what's going on. We're going to put a sequence number right here, and we'll call it 2 because we want this to be the first line. It's got to be the first line to take effect. And generally, when you're writing an ACL or a prefix list, you want your more specific entries at the top of the list to get the desired result. And we're going to do a 16100/16 here at the end. And now let's take a look at that prefix list. See? That's where you have to watch the order of your lines too, because the network 16100 actually matches 2 lines in this prefix list. It matches that second line. It begins with 16. I mean, that would do it. So you've got to watch the order of your lines in a prefix list the same way that you watch them with an ACL. But the great thing is that if you forget an entry, or more than likely you apply the prefix list and you don't quite get what you thought you were going to get, then you can go back and add and subtract lines by using the sequence number. But for the exam particularly, let's keep in mind they increment by 5 by default if you do not configure a number.